We are live now. I think. Yes.
All right, we are.
Rohan is also here. I suggest we take a minute maybe and then start.
Yes, we start whenever
Great.
we want. So good morning, everyone. We are just letting some people getting in.
Hi, Rohan. So,
Good morning, Ruan. Thanks for joining us.
Rohan, maybe we just check your slides just before we start. If you can just share and we verify if everything works.
Okay, great. Just 1 second. Can you see my slide?
Not yet, but something is moving.
They are coming. Okay. So not yet. Maybe you can try another time.
Okay. I suggest we start if you agree.
Okay. So would you like Andre to introduce our webinars?
Great, so welcome all. We greet you on another edition of One World YoungStatS webinar series, part of the YoungStatS project of Young Statisticians Europe initiative of FinStats Association. The project is supported by the Bernoulli Society for Mathematical Statistics and Probability, as well as the Institute of Mathematical Statistics. I will not talk a lot more. At the end, we might announce also the following webinars in approximate Bayesian inference and instrumental variable approaches. But now I give the word to Nina to handle everything and to announce also this webinar and speakers and the discussion. Thanks.
Thank you, Andre. So good morning, good afternoon, and good evening to all our attendees today, and welcome to our today's webinar, which is going to be on theory and methods for inferencing multi-armed bandits, which is a topic that is placed at the intersection between statistics and data science or machine learning. So while our webinars are generally more focused on strictly statistical fields, we also recognize that the cooperation between stats and data science, like machine learning, is very timely due to the spread of a number of machine learning-based real-life applications, which need to come with trustworthy and reproducible results. And more specifically, our today's topic will be centered around the role of multi-armed bandit problems, a field which is currently led by the machine learning community in the space of adaptive decision-making and adaptive experiments. And what's the problem? The problem is that if on one side, multi-armed bandits and more generally, let's say reinforcement learning are acquiring a key role in conducting adaptively randomized experiments due to their potential to enhance participants' welfare while resulting in a more flexible and efficient alternative compared, for example, to traditional fixed experiments. On the other side, there are a number of statistical and inferential challenges that still arise and still limit their application in real life. For example, it is now recognized that traditional inference methods like maximum likelihood estimators or standard asymptotic tests are typically not valid when used in multi-armed bandit collected data, leading to considerable biases that persist even in the infinite data limit and other relevant issues in confidence intervals and hypothesis testing problems. And with this webinar, we aim to offer an overview on the multi-armed bandit problem with its benefits and more particularly the statistical challenges, and then we are going to cover the advances and new solutions for overcoming these issues. Our speakers of today are going to be in order: Anand, which is a PhD candidate in Decision, Risk and Operations at the Graduate School of Business of Columbia University. Then we are going to have Aditya, an assistant professor at the Carnegie Mellon University with a joint appointment in the Department of Statistics and Data Science and the Department of Machine Learning. And then we are going to have Ruhan, a postdoctoral researcher mentored by Professor Susan Atey at the Stanford Graduate School of Business, which is going to start in January 2023, a role of assistant professor in Hong Kong. And thank you for being here. Finally, so last but not least, we are going to have our discussant, Professor Asaf Devi, which is professor and holder of the Gravis Chair at the Graduate School of Business at Columbia University. He is also the recipient of several teaching and research awards, including the Career Award, Columbia University, Career Award from the National Science Foundation, an IBM Faculty Award, a Google Research Award, as well as other several Best Paper Awards, including the 2019 Lancaster Prize. And he has been developing theory and algorithms for reinforcement learning, bandit problems, stochastic optimization, statistical learning, and others. So I'm going to give you the word to you now, and the floor is yours. Anand, I think you are the first one.
Sure.
That is going to start.
I'll just go ahead and share my screen. Thanks, Nina.
Thank you.
Great. Hello, everyone. Thank you to the organizers and for all of you for tuning in from different time zones. I'm very excited today to share our work on, so this is a recent paper that appeared in NeurIPS last year. It's titled A Closer Look at the Worst Case Behavior of Multi-armed Bandit Algorithms. This is joint work with Professor Asaf Devi, who's with us on the panel today. So without further ado, let me dive right into the heart of the problem. So I'll do a quick recap of the canonical two-armed bandit model from statistical learning framework. So it's a very classical model that captures the essence of the exploration, exploitation trade-offs inherent to many sequential decision-making problems. So in particular, this two-armed setting is characterized by two different populations with means mu1 and mu2. We will use the parameter delta to denote the difference, the positive difference between the mean rewards associated with the two populations. It's a very important parameter in the sense that it's a key driver of the statistical complexity of the problem. Just to sort of lay down some concrete notation, we will denote the reward sequence for arm I by the sequence x sub ij, where j is indexed by natural numbers. And it's a standard assumption in literature to sort of have these xi's independent across time and across arms and bounded in 0, 1. So in terms of the goal of this multi-armed bandit experimentation, we're interested in the classical sort of policy objective of maximizing the cumulative expected payoffs over n sequential rounds of play. So the natural question that arises is, hey, what should inform the sequence of these arm pulls in this experiment? So to that end, a policy pi is an adaptive sequence which basically prescribes to the decision maker as to which arm out of 1 or 2 to pull at a given instant of time. Its cumulative regret after n rounds of play is basically denoted by the difference between the optimal mean reward in the problem, which is mu1 by assumption, and the stochastic reward realized at time t. And this is basically summed over the horizon of play. So that is the definition of the stochastic regret that will be sort of coming back to subsequently many times in this talk. The highlighted index here, n sub pi t of t, is simply the number of times arm pi t has been played by the policy until time t. Just to recap, our objective here is minimization of the expected cumulative regret, which is given by this infimum of the class of non-anticipating policies. And just a sort of quick remark, typically a good policy is one which incurs small regret. And to make it more concrete, we basically are interested in the set of policies that are asymptotically optimal, or equivalently, their regret grows sublinearly in the horizon of play. So the expected regret is little o of n, and this is the same as the classical definition of long-run average optimality. All right, so since it's a very well-studied sort of learning theoretic paradigm, there obviously exists a plethora of algorithms that have been studied over the years. Some popular examples include, force sampling-based policies such as explore then commit, then its randomized versions such as epsilon greedy, so on and so forth. Then there are more sort of popular families of algorithms based on this idea of Bayesian idea of posterior sampling, Thompson sampling being a prototypical example of an algorithm from this family. And then we have another family which is based on this principle of optimism in the face of uncertainty. The classical sort of UCB algorithm is a sort of is a keystone sort of member of this family of algorithms. And just to reiterate, the focus of this talk is largely going to be the classical versions of Thompson sampling and UCB. These algorithms are very popular in literature because of the key property to be able to sort of adapt to the complexity of the problem online. Great. So this is, this is what the classical sort of beta prior Bernoulli reward Thompson sampling version looks like. This goes back all the way to 1933. So this very classical algorithm, what this basically does is at any point of time, it basically draws samples from a beta distribution, which is basically associated with each of the two arms. And then you basically sort of end up pulling the arm, which maximizes the sort of Thompson sample associated with either of the two arms. So it's a very simple sort of probably one-line description of the algorithm. Going forward, this is the classical UCB algorithm, which is based on this idea of optimism in the face of uncertainty. In contrast to Thompson sampling, which basically draws samples from a posterior distribution at each point of time, what the UCB algorithm does is it basically maximizes an optimistic estimate of the running mean reward associated with each of the two arms. So in particular, x sub I of t here denotes the empirical mean reward accrued from arm I until time t. And then what the algorithm does is it just inflates it by a bias factor, which is given by square root rho log t divided by the number of pulls of that arm. And then it's a very simple index policy, which prescribes to the decision maker the arm that maximizes this sort of index at any point of time. So a generalization of this policy was actually studied very thoroughly in 2009 in the seminal paper by Audibel et al., where rho basically denotes sort of encodes the exploration parameter of the algorithm. The classical version of the algorithm, which is popularized by the name UCB1, it goes back all the way to 2002, and that actually corresponds to UCB rho with a value of rho that is equal to 2. So the rest of the talk will basically be focused on mostly on the classical version of the UCB algorithm, but then we will make sort of connections to what happens as you sort of inflate or decrease the exploration coefficient. Excellent. So again, without sort of spending too much time on this, since naturally this has been a very well-studied problem in theory, achievable regret and the problem is also very well understood. So there are roughly two regimes in which it's very interesting to look at the problem. The classical easy problems sort of correspond to the fixed delta large sample asymptotics, where it is well known that the achievable regret is logarithmic in the number of samples. And this is actually a rate optimal result in the sense that the lower bound is also known to be logarithmic in the number of samples. It's a very classical result going back all the way to 1985 to the seminal paper of Lyon Robbins. Similarly, there exists a complementary sort of way of looking at the problem where instead of fixing the complexity parameter delta, you fix the sample size n, and then look at the worst case complexity, the worst case sort of hardness across all possibilities, across all instances. So that basically corresponds to this minimax lens of looking at the problem. And again, in this regime as well, the problem has been very well understood in the sense that it is, we know it very well that for classical UCB, the minimax regret is basically upper bounded by square root n up to some sublogarithmic factors. And this is nearly optimal in the sense that the information theoretic optimal rate for achievable regret in the minimax setting is also square root n. Okay, and sort of just to sort of make it clear that, hey, these results are not specific to UCB per se. There exists tons of policies out there which are also sort of rate optimal in a similar sense. In particular, the other algorithm, Thompson sampling, which I'm going to sort of also which we are going to briefly discuss over the course of this talk, it also enjoys similar performance guarantees, both in the instance dependent and the minimax settings. Excellent. So far, I've basically just touched upon what has already been established for this classical two-armed bandit setting in the literature. Our interest in this problem was piqued by this particular sort of question that, hey, we do understand very well the regret behavior of all these, very popular algorithms in the literature, but how well do we actually understand the distribution of arm pools or the distribution of sampling effort across the two arms under any of these popular algorithms? So the question is, how well do we understand the distribution of n1n over n, which is the fraction of times an algorithm plays arm 1 until time n? So the problem here is that existing results offer very limited insight. In particular, it's pretty easy to sort of deduce that for first order optimal algorithms, that is algorithms that are asymptotically or long run average optimal, in the sort of well-separated regime, all first order optimal algorithms guarantee that the sampling effort, which is the fraction of times the optimal arm is pulled until time n, it converges to 1 in probability as the sample size goes to infinity. So this is very well known for a lot of algorithms. But what happens to the limiting behavior of this fraction as delta approaches 0? Just to recap, delta here denotes the difference between the mean rewards associated with the two arms. So a very sort of natural starting point to look into this delta approaching 0 issue would be to sort of pivot to a very simple experimental setup, which is what I'm going to briefly discuss now. So consider a simple two-armed bandit setting where the difference between the mean rewards is 0, gap is 0, and both arms actually yield Bernoulli half rewards, correct? So both populations are actually statistically identical. And then let's see what happens to the sort of empirical distribution of n1n over n under two popular algorithms, Thompson sampling with beta priors Bernoulli rewards on the left, and the classical UCB algorithm on the right. it's pretty evident looking at the graphs that there is something fundamentally different happening between these two, algorithms, as n approaches infinity. And then looking at these graphs, one would naturally be sort of inclined to conclude that these observations will have some serious implications for a lot of settings where these applications, these algorithms are typically just deployed as black box algorithms without really having a very granular understanding of what actually happens at a sample path level. So in particular, the difference between the sort of the empirical distribution, the limiting empirical distribution, is going to have implications in applications where, let's say, algorithmic fairness is a very strong consideration. So for instance, in many settings, to give you an example, I think online advertising would be a befitting example. The goal of the decision maker would be to sort of ensure some sort of fairness between similar competing alternatives. For instance, if there is ad A and ad B, and both are sort of more or less equivalent in terms of their revenue generation rates, then the decision maker might want to allocate the sampling effort between the two advertisements more or less in a balanced manner. And this should happen across all sample paths and not merely an expectation, right? So clearly, this such difference in the limiting behavior of these two algorithms is going to have an implication for algorithmic fairness there. Now, sort of closer to the theme of this Femina series is the sort of the repercussions for off-policy evaluation, or ex post hoc inference, as it is typically referred to. So another simple setting is one could cook up is where you have clinical trials of two similarly efficacious vaccines. So for instance, you have vaccine A, which has, let's say, an efficacy of 79%, and vaccine B, which is somewhere in the neighborhood of 79%, let's say 80 to 81% or thereabouts. Now, as a practitioner, as an experiment designer, you would basically want your adaptive experimentation scheme to be able to learn online the fact that the competing alternatives are more or less similar. And in that case, allocate more or less an equal number of patients to the treatment and to the control groups, right? And this should happen with high probability on any sample path, on any realization, and not merely in expectation. So clearly that there are some implications, that are sort of, that basically sort of hold across a whole bunch of settings. Going forward, I'm going to be sort of focusing more on this implication aspect for post hoc inference. So to sort of to be able to understand this particular aspect better, I'm going to pivot to this very simple sort of quote unquote one-armed bandit setting, where you have a control arm which returns a constant reward of 0.5 every time, and then you have a treatment arm which returns basically rewards distributed as Bernoulli half, right? Now, the estimate of the average treatment effect in this setting after n rounds of play is simply going to be given by this difference. This just denotes the empirical mean reward of arm 2, and the Z statistic associated with this ATE estimator is simply given by 2 times square root of the number of pools associated with arm 2 times the estimated gap, or the average treatment effect. Now, in classical RCT settings, or in classical statistics, we are sort of very well familiarized with the result which says that, hey, in the limit of infinite data, which basically means that as n approaches infinity, the Z statistic is asymptotically normal, correct? Now, however, because we are basically dealing with an adaptive experimentation scheme, we will see some very natural departures from this behavior. So what I'm going to do is I'm going to fix n, which is the size of my experiment. And then I'm going to consider a large number of parallel experiments under these two competing algorithms, Thompson sampling and UCB. So this is what the distribution of Z statistic looks under Thompson sampling and under UCB. For Thompson sampling, we can clearly see that there is some sort of a departure from normality, from asymptotic normality, predicated by the central limit theorem. In particular, we can see some sort of a negative shift in the distribution relative to the standard CLT distribution, which is indicated by the red curve here. And this has a very sharp dichotomy with what you get under UCB. So for UCB, the difference between the sort of empirical distribution and the standard Gaussian is much, much smaller as compared to Thompson sampling, where the gap is actually visible even in the limit of infinite data. What I will show eventually in this talk is that the gap in case of UCB is actually asymptotically vanishing, basically meaning that UCB satisfies asymptotic normality in the limit of infinite data. And this has like some very sharp sort of contrasts with Thompson sampling, for which there have been some recent works, which I'll go through, that establish some sort of a departure from CLT in the limit of infinite data. Okay, so before delving into the main results in this work, I'll quickly go over sort of some instability aspects associated with Thompson sampling. So this is, again, a very simple case where you have two arms, two statistically identical populations. The gap between the arms is 0, and the algorithm under consideration is the classical Thompson sampling algorithm with beta price and Bernoulli likelihoods. For the setup, what we were able to show is that is a rather sort of striking result, which sort of highlights an instability of Thompson sampling, in the sense that so it's an existence result, which basically says that in a two-armed bandit, where the gap between the competing populations is 0, there exists two instances of the problem, such that on one instance you will have the sort of sampling effort on either of the two arms converge to half in probability, which is a very nice result, desirable result, of course. And then at the same time, there will exist another instance of the problem where the limiting distribution is actually uniform on 0, 1. So it's a non-degenerate distribution that arises in the limit. So to sort of graphically illustrate as to what is actually happening here, it's sort of convenient to consider this very simple setup where you have two reward configurations. So consider Thompson sampling in two parallel settings, in two parallel configurations. Configuration 1 is where both arms return a reward that is deterministically 1. Configuration 2 is where both arms return a reward that is deterministically 0, right? And in both these configurations, we are just deploying the classical version of the Thompson sampling algorithm. Again, like usual, we fix n, which is the size of the experiment, and then we do a large number of experiments under this version of Thompson sampling and look at the empirical distribution of the fraction of time the algorithm pulled arm 1 under these two configurations. And we basically end up observing a very striking difference between what happens in the limit. So configuration 1 basically corresponds to the uniform on 0 to 1 limit, which I sort of alluded to previously. And configuration 2 on the right-hand side actually corresponds to this degenerate limit, where the limiting distribution is simply the Dirac measure at half. So this sort of graphically illustrates the previous sort of instability result, which basically predicates existence of instances where you will have such contrasting behaviors under Thompson sampling. Right. So shifting gears a bit, at this point, I will sort of start zooming in on UCB for the remaining sort of part of the talk. So we do have some sort of very interesting dichotomous behavior in the limit of vanishingly small gaps under Thompson sampling. Now, the natural question to ask is, hey, do such observations carry over to UCB also, or is UCB fundamentally different in the limit of vanishingly small gaps between the arms? So in order to sort of quantify or rather study this question better, one needs a precise quantification of what you actually mean by vanishingly small gaps, right? So if you take a look at the sort of well-known sort of bounds for UCB, both in the instance-dependent and minimax settings, one could actually see that these bounds are equal, or they are like equivalent, at least in the leading order, when you have the gap, which is the complexity parameter delta, of the order of square root log n over n, right? So this square root log n over n kind of equalizes the hardness or the difficulty of regret minimization in the problem across these two different regimes, instance dependent as well as the problem independent minimax regime. So going forward, I will sort of refer to this particular regime of delta, where it is basically of the order square root log n over n as small gap. And for delta, that is basically that grows, that is larger than square root log n over n, I'll just refer to those instances as well separated. Okay, so in very sharp contrast to Thompson sampling, what we were able to establish for UCB was this result, which basically says that in the limit of infinite data, as your sample size or experiment size approaches infinity, the asymptotic sampling fraction is constant. It's basically a deterministic constant which can characterize precisely in closed form. So in particular, for small gaps, that is for gaps that are smaller than, I mean, basically square root log n over n, the limiting sort of fraction is half. And that actually increases monotonically from half all the way to 1 through this parametric function that we call lambda rho star of theta. And in fact, this function can be characterized in closed form. And one can actually show that it satisfies some very nice and desirable properties. Namely, it is monotone in theta, which basically means that, hey, as the separability of the instance increases from 0 all the way to infinity along this particular sort of parametric family, the limiting fraction of sample effort allocation on the optimal arm increases monotonically from half all the way to 1 along this particular trajectory. And naturally, the function, the limit lambda star, assumes the value half at 0 and approaches 1 in the limit. Now, this has a very natural contrast with the previous result that we saw for Thompson sampling, where we actually established that a non-degenerate limit under Thompson sampling can potentially arise when you have small gaps in the problem. Okay, so as a very nice corollary of this particular result, what we were also able to characterize was a precise sort of characterization of the worst case regret of UCB. So in particular, what I mean by that is in the square root log n over n regime. So in the regime where theta is asymptotically equivalent to this modulo some constant theta, the stochastic regret, just to re-emphasize, this is not the expected regret, but the sample path dependent stochastic regret of UCB. It follows the sharp asymptotic that if you basically normalize it by square root n log n, it approaches a constant in probability asymptotically, and that constant can again be characterized in closed form. As a natural byproduct of this result, you have you have this very precise characterization of the worst case expected regret of UCB, including the exact numerical constants that are achievable in the worst case setting. So just to sort of zoom out a bit and sort of compare this with classical results in the literature, it is well known that the information theoretic optimal minimax rates for the bandit problem is square root n. What we're able to establish for UCB is that there's a non-trivial departure from this information theoretic optimal rate, under UCB. So the gap is actually not vanishing, and this has a very sort of natural connection to the previous best known upper bound for UCB, which basically established a big O of square root n log n regret. It was actually an open problem in the literature as to whether the square root n log n for UCB was strictly unimprovable in terms of its dependence on n. And what our result basically says is that, hey, yes, this rate is actually tight. This is actually theta of square root n log n, and in fact we end up characterizing the precise constants that are sort of that encode the worst case complexity of regret minimization under UCB. Now, what that actually translates to graphically is this following sort of contour plots. So these curves here basically sort of represent different complexity levels of for regret minimization under UCB. So the h sub rho of theta function here is basically the constant that arises in the limit here, and we basically show that the h sub rho of theta function is unimodal in theta, and the theta star and h of theta star points actually correspond to the worst case achievable regret for UCB, which one can precisely characterize up to numerical constants, in fact, including numerical constants. Okay. So that was so far as the worst case sort of behavior in terms of expected regret of UCB was concerned. Shifting gears slightly at this point, one could ask a natural follow-up question that, hey, you could establish basically some of these granular results when the separability of the instance is vanishingly small. Is it possible to characterize, is it possible to sort of come up with a sharper characterization perhaps at a distribution level or perhaps at a process level for the two-armed bandit problem under any of these two algorithms, UCB or Thompson sampling? And this is where we sort of pivot to this classical diffusion scale analysis. Now, this analysis has been sort of very common in the operations research literature, especially sort of pertaining to queuing theoretic systems, where it's sort of well established that the queuing problem admits very well-known diffusion limit solutions in what is called the quote-unquote heavy traffic or the quality and efficiency driven regime, where the traffic and density of the queuing system basically scales as 1 over square root n. Now, if you look at this 1 over square root n sort of expression, this has some very natural connotations and connections to learning theory and, in particular bandits in this particular instance. We actually know that the information theoretically hardest instances have gaps that scale as 1 over square root n. So sort of just trying to sort of, establish some parallels between the diffusion limits for queues and diffusion limits for bandits. A natural question is, hey, we know that well-established sort of well-known diffusion limit solutions exist for queuing systems under the heavy traffic regime. Is it possible to establish some corresponding results for bandits also under a similar scaling of the complexity parameter? And we actually were able to answer that question affirmatively in this work. So what we do for UCB is, come up with a diffusion limit characterization of the regret of UCB. So sort of more specifically, the diffusively rescaled cumulative reward process, which is given by R sub NT normalized by square root n. And this is actually a process indexed, indexed by T in the interval 0 to 1. We could actually show that this converges in distribution in law to this Wiener process with a drift of C over 2, which basically just encodes the hardness of the instance, and this dispersion parameter, which is a function of the reward variances. So I mean, this is, I mean, we're in fact quite sort of astonished to sort of see such a result here, because what it basically says is that, hey, in the limit of infinite data, a two-armed bandit system under UCB is asymptotically equivalent to a classical system where the sampling is non-adaptive. So this basically sort of proves a version of Donskoy's theorem or the functional central limit theorem for the classical UCB algorithm, which we found was found to be somewhat remarkable. And similar results, similar diffusion limit results can in fact be established also for the cumulative reward processes associated with each of the two arms, and not only the regret process. So we have this very nice diffusion sort of limit characterization of UCB. One could also ask that, hey, you perhaps got lucky with UCB. Can you pull up something similar for Thompson sampling or for other versions of the algorithm also? So we were, luckily there was this contemporaneous stream of literature, by Stefan Wagger et al. And Peter Glenn et al. At Stanford, who basically characterized the diffusion limit for the Gaussian sort of the Gaussian prior and Gaussian likelihood-based version of Thompson sampling in terms of solutions, potentially multiple solutions to a system of stochastic differential equations. So it's a very nice piece of very recent work, which I would sort of which I would refer to for for a more comprehensive understanding of what happens in the diffusion limit under Thompson sampling and how it is different vis-a-vis UCB. All right, so I would believe this would be a natural stopping time for for taking questions. I basically sort of I gave you a very quick overview of what the paper is about and sort of covered some questions that we've that we basically unpacked in this work, and I'd be very happy to take questions from you at this point. Thank you.
Thank you, Anand. Thank you very much for your great talk. I invite everyone to type their questions in the chat. I also have some questions, but if that's okay for you, I will move forward with the next speaker, and then we can have a joint discussion at the end, so we can allow also the audience to participate. Thank you very much.
Thank you.
And so I will then invite now Aditya to present his talk, and thank you very much for those who are attending. So please, Aditya, the floor is yours.
Great. Thank you very much, Nina. And Anand, that was an excellent talk. So you've set a high standard for me to try to meet. So my talk's going to be about how to perform safe anytime valid inference, and I'll explain what that means in the face of 3 different sources of bias in bandit data analysis. As Nina mentioned earlier, I'm a faculty jointly in the Department of Statistics and Machine Learning at CMU. Since this is targeted at young audience members, I'm always looking for postdocs. And I just also want to acknowledge support from the career and a couple of research awards. There's some work that's done with faculty members, but I wanted to highlight the younger members whose work will appear in this talk. And that's Jae-Hook Shin, who graduated recently from CMU, is now at Google. Steve Howard, who graduated recently from Berkeley, now at LinkedIn. And Ian, who's still my student at CMU. Okay, so the sample mean. Okay, so this is just mostly notation settings. So let's imagine that we have little n samples. Let's call these xi from some univariate distribution P whose mean mu actually exists. Then mu hat is going to denote the sample mean, and in classical statistics we like the sample mean because it's unbiased, it's minimax optimal for appropriate loss functions like the squared loss, it's consistent, meaning it converges to the mean and converges almost surely, and so on. But the question that we're going to answer in this talk and think about more carefully is what happens when the data are actually sampled adaptively. Okay, do all these properties hold, and if not, how do they break down, and how should we correct our inferences accordingly, and so on. Okay, so here's what I want you to think about in the back of your heads. This is what I call the counterfactual view of a multi-arm bandit experiment. So here, just the arms, the actual labels don't really matter. So there are just some labels, 1 to k for the arms. So arm 1 has some distribution P1 with mean mu1, and arm k has distribution Pk with mean mu k. And so the means are this way, and then time is going vertically. Now, what I want you to imagine is that at the very start of the experiment, before we've collected any data, actually in the background is sitting hypothetical data that you could have potentially collected from every one of these arms. So you can imagine that we sample all the arms infinitely. There's nothing bandit going on. This is all done at the very start of the experiment, but we don't observe it. This remains hidden in the background. Now, at time 1, let's say we pull arm 1, what we actually observe is x star 1, 1, and the rest of them stay unobserved in the background. Let's say at the second step, we pull arm k, and we observe that, but the rest of those elements in that row remain hidden, and so on. So this is what we call adaptive sampling, meaning based on the data that we have seen so far, we choose what to sample next. Now, another common thing in bandit experiments is we don't know how much data we want. Like, are these arms very similar? Are they very different? If they're very different, we can stop early. If they're very similar, we might have to collect more data. And so there's often adaptive stopping, and I'm going to call that stopping time tau. And then, okay, let's say we stop the experiment. We have these sample means from each of the arms that we have collected, but typically we are not interested in all of them. So imagine now that there's a particular arm, maybe the one with the largest sample mean, that looks very interesting to you. Maybe this corresponds to the best treatment. So there's an adaptively chosen query arm. And so that's going to be represented by kappa. So k corresponds to a fixed index, but kappa corresponds to a random index, in the sense that this index kappa is dependent on the data. And only after seeing the data, I realize, oh, I'm interested in arm 3. And so I'm going to try to stick to this color scheme as much as I can. We'll see if I succeed, but red is going to talk about adaptive sampling, green about adaptive stopping, and blue about adaptively choosing an index that you care about. And each of these will introduce a separate source of bias, and actually it's quite interesting to understand these sources of bias. So, the broad question is, how good is mu hat kappa of tau, the sample mean at the stopping time of an adaptively chosen index, as an estimator of mu kappa? Remember, this is a random target because I don't even know in advance which arm I'm interested in. So kappa, this mu kappa is a random target that is a data dependent target arm. So here's going to be the summary of what I'll tell you in the next 25 minutes or so, is that the bias can actually be of the same order as the square root variance. And so usually maybe for the sample mean, we think of it as unbiased, and then we talk about its variance, but here actually the bias and the variance the square root variance can be of the same order. The sign of the bias is quite subtle. Like, you might be under or overestimating it, and we'll discuss that. And even the magnitude is quite subtle. If you want valid confidence intervals at arbitrary stopping times, there is no option but to use confidence sequences. This is a necessary condition that I will delve into. And if you don't want to do estimation, you want to do testing, you can invert these confidence sequences to get what are called anytime valid p-values or e-values. And these would be tests that are valid even under continuous monitoring. Okay, so now I'll get into each of these themes. So the outline is, in the first half, I'll talk about the bias, and the second part, I'll talk about the bias and variance together. So I'll talk about first the effect of just adaptive sampling and, just in pictures, the effect of only adaptive index, only in pictures, the effect of stopping only in pictures. So I'll kind of separate these three sources initially, and then I'll tell you what happens when you put those three together. And those are just going to be qualitative, talking about the sign of the bias. The second part, I'll talk about, the actual quantitative bounds on the bias, and then get into what is a confidence sequence and how do we construct these anytime valid p-values and so on. Okay, so here's, the three takeaway messages that are going to come. So the first one is for adaptive sampling. Adaptive sampling leads to a negative bias. Okay, so if we prefer arms with higher observed rewards, that's what adaptive sampling means. Typically, if there's a good arm, we sample it more often, a bad arm, we sample it less often. This leads to a negative bias. Okay, but there's some subtleties, and let me explain that now. But let me explain intuitively why should you expect to see a negative bias due to adaptive sampling. So this is a picture to keep in mind. Think about just one arm for the moment. This is a single arm, and it's the jth arm. And let's say this dotted line is its true mean mu j. And on the x-axis is the number of samples we have collected from that arm. For simplicity, just think about this as a Gaussian. None of this will really matter. It's really valid non-parametrically, but for simplicity, think of this as a Gaussian with mean mu j. Now, what's going to happen is I'm going to show these two alternate realities, and we'll see how the algorithm behaves in those two realities. So in the first reality, the sample mean at some point of time t is above the true mean. This is just random noise. It's never going to be exactly the true mean. And let's say that it's above the true mean. And in the other alternate reality, it's below the true mean. Now, in the first reality, you think, oh, this is a good arm. Let's sample it some more often. Let's get some more samples from it. And so you sample it more often. But in the other alternate reality, you think, it's not such a good arm. I don't want to sample it very often. And so the thing is, when you sample more often, well, almost by the law of large numbers, the sample mean must converge to the true mean if you actually did sample it infinitely. So what's going to happen is that this is going to pull down, if you sample it enough, it's going to pull down the sample mean towards the true mean. But in the other case, you don't give it a chance to recover. So if you were unlucky in the first few draws, it doesn't recover as much. And this is why there's a net negative bias. You should think in these two alternate realities. If I go higher, I get pulled down, but if I go lower, I don't get pulled up as much. This leads to a net negative bias. And so there's this paper a few years ago that was titled "Why Adaptively Collected Data Have a Negative Bias and How to Correct for It" by Ni et al. But here's a really, really critical point. This is only valid for a fixed arm j and a fixed time capital T. Okay, so this is actually not true for chosen arms kappa and stopping times tau. This is not true. And so actually that title of that paper I find very misleading, and I'll tell you why in the next slides. Okay, so this is adaptive sampling only. So now let's think for a moment about adaptive stopping. Turns out that adaptive stopping leads to a positive bias, not a negative bias. So what is adaptive stopping? If observing higher rewards results in you stopping sooner, that actually corresponds to a positive bias. So for now, again, forget about adaptive sampling and adaptive choosing. Think about a single arm. It's simplest for this notion of bias. So you're just looking at arm J, and you're going to sample until some stopping criterion is met. So here I'm in green as a curve, drawn the stopping criterion. What this really means is if the sample mean ever crosses this boundary, you'll stop. Or in this case, this vertical line means if I reach this maximum time, I stop. Okay, so one of those two things happen. So now again, there's these two alternate realities. In one of them, I get lucky with my first set of draws, and wow, I hit the stopping curve, I actually stop. There's no chance of it to recover. But if I was actually, unlucky and I got, lower set of draws, well, I'm not stopping. So I'm going to sample it some more often. I'm going to recover to some extent until I hit some stopping criterion. Could be the maximum time or could be the curve. And these two alternate realities are kind of competing against each other. And this leads to a net upward bias. Okay, so this actually was noticed earlier by Starr and Woodruff in '68. If the mean exists, a very simple result, okay, it's really clean. If the mean exists, if tau is almost surely finite, the stopping time is finite, and then the bias is always positive for any upper stopping curve. So the form of this curve doesn't really matter. Like any upper stopping curve that you draw, the bias is going to be positive. And in fact, Siegmund in the 70s also showed that for some types of curves, and if it was a Brownian motion, then you can actually calculate even the magnitude of the bias a little bit. But essentially, if you look up the sign of the bias, adaptive sampling and adaptive stopping lead to opposite signs of bias. What about the third one, adaptively choosing an arm? This typically, again, leads to a positive bias. So if higher observed rewards make an arm more favorable, more likely to be picked as the index of interest, then you're going to have a net positive bias. So again, to understand the role of choosing an adaptive index, forget about adaptive sampling and adaptive stopping. Let's say there's no adaptive sampling, there's no adaptive stopping. I just choose an index adaptively. Why is there a positive bias? It's very easy to see. Think about the setting where you have k arms and all of them are Gaussian with the same mean. I pull all of them the same number of times. There's no adaptivity in sampling and stopping. So what's going to happen is this is the true mean mu. Now the x-axis here is index, by the way, not time. So these are the different arms. And I pull all of them like 5 times and I stop at a fixed time. And these are the actual, sample means that I observe. Well, that sample mean looks the most interesting to me. And so, let's call that index as kappa. Then what you can write down is that for any fixed k, actually the sample mean is unbiased because there's no adaptive sampling and no adaptive stopping. So for any fixed index k, the expected value of mu hat k minus mu k is actually 0. But for kappa, your adaptively chosen index, the bias is actually positive. Clearly in this case, the true mean was mu. You picked something that was larger. The expected value of mu hat kappa minus mu kappa is of the order of square root 2 log number of arms, which is actually positive. Because it's just intuition for why picking good indices to look at later leads to a positive bias. Okay, so negative bias from sampling, positive from stopping, positive from choosing. So now you can actually mathematicize all of this. So what do I mean by an optimistic sampling rule? I mean that the number of samples from that arm at a particular time is actually an increasing function of, remember that first counterfactual table, of the samples from that arm. So it means that if I see higher values, I am more likely to sample from that arm. That's called an optimistic sampling rule. An optimistic stopping rule is when I stop sooner when I see larger samples, so it's a decreasing function. And optimistic choosing is my likelihood of choosing a particular index is an increasing function of that data. Larger values lead me to be more likely to be choosing. So our theorem in the paper is that as long as the means exist and the expected stopping time is finite, any optimistic sampling rule, the bias is always negative. Any optimistic stopping rule, the bias is always positive, and any optimistic choosing rule of the index, the bias is always positive. But the interesting thing in multi-arm bandits is typically all three exist at the same time. So we do have a more general theorem in the paper that talks about what happens when all three exist at the same time. But I want to give you an example of a result that comes out of it as a corollary. Is that for the LIL-UCB algorithm for best time identification, all three biases apply. We sample adaptively, we stop adaptively, and we choose the index of the arm that has the largest sample mean. You can prove that actually the net bias of the chosen arm is actually positive, which is a very different conclusion from the title of that earlier paper. And the reason is that stopping and choosing introduce biases in the opposite direction from sampling. Okay, so this is all to suggest that understanding bias in multi-arm bandits is actually pretty subtle, and you have to account for all three sources. Okay, so what about quantitative bounds? So I've only told you about the signs so far. How large can this bias be? So let's first talk about a fixed index k, but what happens under both adaptive sampling and stopping. So let nk of tau be the number of samples from arm k, by the time I've reached my stopping time tau. I'm going to define this quantity, which turns out to be the key quantity of interest, is the effective sample size. Now, the effective sample size is not the expected value of this quantity. It turns out it's the expected value of 1 over that quantity, and I take the inverse. That's actually the thing that ends up mattering. So here's a theorem. As long as, well, I sample at least b times, b could be 1. So I shouldn't stop without even sampling an arm. That's it. Then the squared risk, that is the error between my sample mean and the true mean, that squared risk is bounded by sigma square is just the variance, and I get a log n effective by n effective. So if you ignore the log term for the moment, it's really like this n effective is what really determines the risk, if you want, of this method. And this actually does recover even without any adaptivity. This is the rate you should expect to see, except for this kind of log factor. And in the case where there's no adaptivity at all, n effective is equal to n. So if there's nothing adaptive going on, n and tau are both non-adaptive, then capital N is equal to little n, and so on. And you can prove that you cannot replace the denominator by the expected value of n. So if you're wondering, could you have proved this theorem with expected value? No, we have counterexamples in the paper where that's just false. And kind of as a corollary, kind of to go along with the squared risk, you also get that the bounds on the bias are actually given by this order. So it turns out that you can quantify the bias also separately. And this is tight. So this is not just an upper bound. We can prove that for a stopped Brownian motion, even in the one-armed case, you do actually get a bias of exactly this order, except for that log factor. Okay, you can improve this to include choosing also. So if your index of the arm is also adaptively chosen, now meaning that you also pick an arm kappa adaptively, then, well, as long as you've sampled every arm at least 3 times, this 3 is just there for a log term. Then what you can show, this is written slightly differently, but here n is random. So I've taken it to the left-hand side to write the expected value of n times the squared risk. And on the right-hand side, you have these 3 terms. One of them is a mutual information between your rule for choosing kappa and the actual, data. And here's basically a log kind of term. So a similar result to before, and past work on adaptive choosing says if I don't have adaptive sampling and I don't have adaptive stopping and I just pick my index kappa adaptively, then there's a paper by Russo and Zhu that says that this expect value of n times this looks like the same term. So our result basically generalizes theirs to including, this is not in a multi-arm bandit setup. I fix there's no sampling or choose or stopping, but our work basically generalizes this to a multi-arm bandit setup at a price of basically a log factor. Okay, so this gives us some handle on how large these biases can be and so on. But actually, if you want to do tests and confidence intervals and so on, you need not just a handle on the bias, you need a handle on the variance and things like that as well. So what is the problem? Like, why is this difficult? And the difficulty is that in multi-arm bandits, we typically have continuous monitoring, meaning that because we look at all the data to decide, like any algorithm looks at all the data to decide which arm to sample next. That's basically looking at your data continuously as you monitor it, often also to decide when to stop. So you collect some data. Maybe, if you've heard of this, p-values, we often peek at our data. We might check if our p-value based on n samples is less than alpha or not. Alpha is some predefined error limit. If it is, then you stop and you report. And so this is called optional stopping. But if it's not, you continue and you say, I want some more data. And then I peek again. And this kind of goes on until you get a p-value that's actually less than alpha, in which case you stop. And so this is an issue because with commonly taught p-values, things coming from t-tests or things of that kind, the false positive rate is going to be much larger than alpha for this procedure, coming out of optional stopping. So here's a mathematical way to state that. So let's say Pn is a classical p-value, like a t-test, calculated using just n samples. Now, what does it mean to be a p-value? It means that under the null hypothesis, let's say there's no treatment effect or something of that kind, what you have is that for all sample sizes, the probability, or if it's asymptotic, then as n goes to infinity, but you can also construct non-asymptotic p-values using permutation tests, then the probability of Pn being less than alpha is less than alpha. This is the probability of a false positive, because when you see a small p-value, you claim a discovery. The probability of falsely claiming a discovery is at most alpha. That's what it means to have a valid p-value. But now what we're really seeing is that tau is the stopping time of an experiment. Tau depends on the data. Often in the cartoon I showed you on the previous slide, tau is the first time at which my p-value was less than alpha. Unfortunately, the probability that p tau is less than alpha is not less than equal to alpha. So this really only holds at fixed sample sizes. It does not hold at stopping times. And in fact, the probability that there exists some time at which Pn is less than alpha could be much larger than alpha. And so the difference between validity at fixed times and validity at stopping times is a bit subtle, but that's where all the errors are coming from, often in psychology and adaptive collection of data without really correcting for the adaptive collection of data. Now, people in psychology have often suggested, oh, let's throw away p-values. I don't like p-values. We should move to estimation, move to confidence intervals. This is a mistake. The same issue occurs with confidence intervals. There's a duality between p-values and confidence intervals, and like magically the problem doesn't disappear by throwing away p-values. So this is misguided. So what do I mean by that? So if you collect data and make decisions based on your confidence intervals, if you collect and you check if your 1 minus alpha confidence interval doesn't contain 0, and that's your stopping rule, your confidence interval could be for the treatment effect. And if not, you collect some more data and so on. Again, the false positive rate is strictly going to be larger than alpha. And the math goes through in an analogous way. If you let ln or un be any classical 1 minus alpha confidence interval, you construct using the central limit theorem or something of that kind, using the first n samples of your data. What does it mean to be a valid confidence interval? So suppose your treatment effect is theta, that's what you're trying to estimate. Then a property of a confidence interval is that for any fixed sample size n, the probability that theta lies in ln un is at least 1 minus alpha. This is a good event. This is the probability of coverage. And I have at least 1 minus alpha probability of coverage. But again, as before, if tau is the stopping time, again, tau might depend on the data. For example, you might stop collecting data when your lower confidence bound is above 0. You might choose to stop then. It is not the case that the probability that theta lies in L tau U tau is at least 1 minus alpha. That's not true. It's only true at fixed sample sizes, not at stopping times. And in other words, if you ask, is it true that for all n theta lies in ln un? And the answer is no, it could be much less than alpha, and in fact, usually 0. So moving to confidence intervals does not get rid of the problem. Okay, so what does? Its answer is a confidence sequence. A confidence sequence for a parameter theta, it could be theta t, meaning the parameter you're covering could itself depend on time, but if you want for simplicity, think about a fixed parameter that you're trying to cover. A confidence sequence for theta is a sequence of confidence intervals LT, UT, where T indexes the number of samples I've collected, and it has a uniform simultaneous coverage guarantee. Okay, so this is what the coverage guarantee looks like. It says the probability that for all t simultaneously from 1 to infinity, theta lies in LTUT is at least 1 minus alpha. Okay, so this is a very strong coverage guarantee. It was introduced by Robbins and his collaborators, Lai and Sigmund. They're still at Stanford, and Robbins was like one of the leaders of this long ago. Kind of lost interest in the mid-80s, but in the last 5-10 years, it has gained a lot of interest back again. So that's what a confidence sequence is. If you want to see the difference, it's much stronger than a pointwise or fixed sample confidence interval guarantee, where this for all being inside the probability makes a big difference. In usual confidence intervals, you learn about the for all n is outside the probability, and this does not, this does not hold under optional stopping, and this is valid under optional stopping. Okay, so this is what you should look, here's a visual example of a confidence sequence. So here, time here is on some kind of a log scale, and I'm plotting, this is from a causal inference paper, but we have a confidence sets for the average treatment effect as I collect more data. And what you're seeing in green over here is a classical like central limit theorem based confidence interval. That's what's in green. The dotted gray line is the truth. That's the actual truth, because this is a simulation. And the orange line is our confidence sequence that we construct. And so the one thing to note, the main difference is this CLT is not valid. These confidence intervals are not valid under adaptive stopping. So if you were continuously monitoring this, you might stop at some point, and you can think about this as 0 if you want. You might get very excited at this point and say, stop, I have evidence that my confidence interval is above 0. Let me proclaim a discovery, and you would be wrong. And so you could be wrong multiple times actually with the CLT based confidence interval. But the property of a confidence sequence is this orange band. It's simultaneously over all time will always contain this gray dotted line, the ground truths. Another way of viewing that, which is on the right-hand side, is the cumulative miscoverage rate, which is if I repeat this left curve is one run of the experiment. The right curve is if I run the experiment on the left 10,000 times and I tell you how many times did I make a mistake up to a particular point in time, you'll see that the confidence sequence, the total mistake probability is at most 0.05 from 1 to infinity. But central limit theorem, you will, I mean, if you peak at usual confidence intervals, you will make a lot of mistakes in your experiments. And so this is not a small issue. This is pretty much guaranteed in the sense if you run this till infinity, this will go to 1, meaning you will make a mistake with a central limit theorem based confidence interval or any confidence interval, nothing special about the central limit theorem. And you can construct these confidence sequences also for time varying quantities. The treatment effect could depend on the people who have entered your trial so far. And so that's why there's a theta t, and you can construct confidence sequences for theta t as well. And so, you know, you don't have to think about covering a fixed quantity over time. Okay, so what are the implications of a confidence sequence? Here I've written the same guarantee of a confidence sequence, but inverted it so that you get used to thinking about it both ways. This is written in terms of error. It says the probability that I ever make an error at any time n is at most alpha. So some implications, the most important one is valid inference at arbitrary stopping times. For any stopping time tau, the probability that theta does not lie in L tau U tau is at most alpha. So this is if you have a confidence sequence, this fact is true. But post hoc inference in hindsight is also true. You can ask about other random times which are actually not stopping times, and the coverage guarantee will still hold. And the most important fact is you don't have to pre-specify your sample size. You can extend your experiments adaptively. You can stop earlier than you thought you would, and your inference will always be correct. Now, the key part is the above properties actually all imply each other. They're equivalent. Okay, so if you want valid inference at stopping times, only confidence sequences, are valid. They're the only tool that you can use. These meaning that property 1 implies the property at the top. They're all equivalent. So any CLT you see in the Bandit literature is invalid under optional stopping. It only holds for fixed sample sizes that go to, and I increase the fixed sample size as I go to. And this is really critical. In the 60s, people made a big deal of this, and Anscombe's central limit theorem and many other central limit theorems talked about the difference between does the central limit theorem type result hold for fixed n as it goes to infinity or for stopping times as they go to infinity. And those are very different regimes to study. If you really want valid inference at stopping times, confidence sequences are the only way, and not asymptotics. Okay, here's an example of a visual, what it looks like, mathematically. I showed you some visuals earlier. Here's an example of a math formula. So if xi is Gaussian, or let's say bounded in -1,1, sub-Gaussian, things like that, then a confidence sequence will typically be centered at the sample mean, but the width will be slightly different from your usual confidence intervals. It'll still have like a log 1 over alpha kind of dependence on the error probability alpha, but instead of scaling like 1 over square root n, it'll scale like log n by square root n. So like there's this additional price, and that's coming from the law of the iterative logarithm. That's the price you pay for adaptive peaking and so on. Now, there's a duality between anytime valid p-values and confidence intervals. Okay, so I've told you how to construct confidence sequences, they're also called anytime confidence intervals. If you say I don't want confidence intervals, I actually want a test, that's fine. You can get an anytime valid p-value from that confidence interval. So if you define your set of null values for theta as script h0, so this could be less than equal to 0 is my set of nulls or something of that kind, then you can define pn as the smallest alpha such that the 1 minus alpha confidence interval does not intersect the null. So you construct confidence interval that different values alpha, and the smallest alpha that the confidence interval does not touch the null, that's a p-value. So if you use a pointwise confidence interval, then pn is a classical p-value. That's the usual inversion between p-values and confidence intervals. But if you use a confidence sequence or an anytime valid confidence interval, then what you get is an always valid p-value, which means that this p-value is actually valid at any stopping time. For all stopping times, the p-value is stochastically larger than uniform under the null. Okay, so here's like I'm starting to rack up. We can actually construct confidence sequences and always valid p-values in a wide variety of non-parametric settings. We can also incorporate prior information about expected signal strength, and we can extend all of these tools to multi-arm bandit settings and sequential causal inference, both randomized and observational. Okay, so yeah, I am wrapping up. Here's a summary of what I said before. The bias can be of the same order of the square root variance in bandits. The sign of this bias is very subtle and its magnitude too. Valid confidence intervals at arbitrary stopping times requires the use of confidence sequences. You can invert these to get anytime valid p-values or e-values, which I didn't mention. And these give tests that are valid under continuous monitoring. And so confidence sequences essentially account for both bias and variance. And they allow you to make what I call safe anytime valid inference, which refers to the ability to make inferential statements, p-values, e-values, confidence intervals that are provably valid under continuous monitoring and enable the use of flexible stopping or continuation rules. Okay, so again, acknowledge my collaborators here. Here's a list of papers where I talked about these topics. So the first couple are about the sign of the bias at ICML and NeurIPS a couple of years ago. The third one talks about the magnitude of the bias. This one introduces non-parametric confidence sequences in some generality. We've extended this to off-policy confidence sequences as well, which is of interest in bandit settings. And the last one over here talks about causal inference, confidence sequences for causal inference. You can find these on my webpage as well. For those who are interested, we still have a few slots open at a workshop on these topics, safe anytime valid inference, which is at the end of this month. So if you like these topics and if you can somehow make it to Netherlands by the end of this month, then we have a few slots open at our workshop. Okay, I'll stop with that and thank all of you and be happy to answer questions later on.
Thank you, Aditya. Thank you for the great talk and for sharing this webinar, this course that you're going to take. And again, I invite the audience to write your questions in the chat, and we are going to try to answer those questions at the end. So now I'm going to give the floor to Ruhan. So please, Ruhan, the floor is yours.
Thank you so much.
Thank you.
Can people see my slides now?
They are coming. Yes.
Oh, can I advance my slides?
Perfect. Yes.
Okay. Thanks. I just get started. Thank you for having me to this webinar, and it's great to learn from people who are in similar fields. I really enjoyed previous talks. Right now, I'm going to talk about our work on how we do inference using data collected adaptively. But here, I just want to mention that we are not considering adaptive stopping time. We are not considering adaptive choosing arms, just as Aditya talked about. We are only considering adaptive sampling, as I will discuss later. So firstly, I want to acknowledge my wonderful collaborators, Rita, Skip, Stefan, and Susan, and the talk will feature on the two papers listed here. So since the topic is about adaptive experiments, let me first introduce what are adaptive experiments. As composed to their randomized controlled counterpart, the adaptive experiments are sequentially randomized experiments, which include bandit algorithms. So the experimenter may adjust the data collection mechanism during the course of the experiment in response to the experimenter's past observations. For example, the experimenter can change the data collection policy to maximize the cumulative reward, just as bandit algorithms during the experiment. Or it can also she can also adjust the policies to quickly identify the best treatment arms, for example, to drop samples around the potentially optimal arms. And also she can also change the policies to maximize the power of a particular hypothesis. That is to say that adaptive experiments are sample efficient for some particular objectives. And as an example here, which also echoes the 11th example, consider a clinical trial, and we have 4 drugs. At the beginning of the experiment, the experimenter may not know which drug performs best, and she wants to get more information to inform the later practitioner or the policymaker. So at the beginning of the experiment, since we have no knowledge, the drug may be assigned to the patients randomly at uniform, which means each drug will get probability 1/4 to be assigned. But over the experiment, the experimenter may collect more and more samples. For example, here, the drug 2 performs better as compared to other drugs. So more drugs may be assigned to, more patients may be assigned to drug 2, and just with the objective to maximize the patient health here. And the whole process is a sequentially randomized experiment, and which can be and given the adaptive data here, the hospital data, the analyst or the doctors want to evaluate the drug performance on different patient groups. But this is not easy, especially if the experimenter is too aggressive. For example, the experimenter is too finds that certain drug does not perform well at the beginning of the experiment. So this drug gets abandoned in the middle of the experiment, which means we do not have enough samples around this drug, and we cannot evaluate its performance relatively well. And in this talk, we will show like how we fix this problem if we still want to evaluate different drugs' performances. And if here as we have seen from the previous talks, the sample mean estimators can have a lot of problems. But here we will introduce another type of estimator, and we will show how we can use the sample reweighting to hopefully give us a more accurate estimation of each drug performance, as well as we can construct the frequency-based confidence intervals using asymptotic normality. But again, here, I just want to note that we are not considering adaptive stopping time, which means that the sample size is fixed and the data is given, and we just want to evaluate a fixed policy or fixed arm. Let's formulate the previous adaptive experiments in a more mathematical way. Consider the contextual bandits at each time t, the experiment collects data xt, wt, yt. Xt here refers to the patient characteristic, such as the age and gender, which is sampled from a fixed population. And here, an experimenter may have some data collection mechanism which determines the different arm assignment probabilities. And we use ET to note these probabilities. And ET here, ETXT here is a probability vector that will, such that the arm or the drug in our previous example will be sampled, subscribed to a categorical distribution specified by ET here. And note that in this scenario, we do not include. We mainly consider the ET to be a probabilistic vector, and we not consider the scenarios that such as UCB algorithms that ET is an indicator function, is a deterministic vector here. And these assignment probabilities in an adaptive experiment can be updated over time based on the past observations. So in our example here, the experimenter will prescribe the drugs in response to the drug's previous performances. And we also assume that the potential outcome framework, that is the patient's responses when the patient will prescribe to the different drugs. This is YT1 or to YTK here, but note that we only observed one outcome from the assigned arm or the prescribed drug, which is YTWT here. And here we assume that the environment is stationary, that is the WT, XT, YT1 to YTK are ID sampled from a fixed distribution. But our data, XT, WT, YT, is neither independent or identically distributed, since WT may depend on the past observations, and that is where adaptivity brings problem here. And a policy pi here specifies the arm assignment rule. That is, how do we map the context xt to a probability vector pi xt, which will instruct how to select arms. And the policy value is defined as the expected value that can be attained when the arms are assigned in accordance with the policy pi here. And our goal here is that given the data collected adaptively from the contextual bandits, and later on I will also discuss the multi-armed bandits, and given a policy pi, which means we do not consider the adaptive arm case discussed by the data, and we just want to estimate the policy value Q pi, and we also want to construct the confidence intervals around our estimation. So this is a problem setup here. Yeah, as we have seen that there are a lot of previous methods which have studied this problem previously. The first noted one is named as the direct methods, and the sample mean estimator is one of them. And so here, the direct method fit a regression model mu hat to estimate the arm value, which the expected arm value here, and the mu hat is fitted on the observations that were assigned to the specific arm W. And when it comes to estimating the policy value, it replaced the previous potential outcome YTW here by the mu hat XTW to estimate the potential the total policy value under this framework. And as we have seen that by adaptivity, this estimator can be biased. But how do we address it? A simple approach and also a very intuitive approach is to reweight the samples based on following the principle of the importance sampling, and this is named as the inverse propensity weighting. And here we adjust the sample weights by the inverse propensities here, inverse probabilities here, 1/ET. And from simple algebra, you can calculate, this one is unbiased for the policy value. But this one can have very large variance, since by adaptivity, certain arms will be dropped eventually, and this ET may decay to 0 over time, which means the denominator can be very small when the T is large, and so that the whole quantity can have very large variance over time. So how do we fix it? So this records to the problems I just discussed with the direct method, and also the IPW estimator. The left plot is the performance of the sample mean estimator, which is one of the direct methods, and this is also consistent with the NS example here. So and also so here this is biased downward. And the right panel here is for the IPW method, and as we can see that this one is unbiased, but this one has large tail and has large variance. So how do we fix it? In causal inference literature, people usually discuss another method which combines the previous two methods, which named as augmented inverse propensity weighted estimator. So here, this estimator is a weighted average of this AIPW score gamma hat t here. Gamma hat t here also use the direct method estimates, which is mu hat here, and also the inverse probabilities, the 1 over ET here. But the inverse probabilities are only applied to the bias correction term YT minus mu hat here. Note that the mu hat can be biased, as we have learned from previously. So the YT minus mu hat is a biased correction term here. And the inverse propensities are adjusted to this bias correction term to adjust this ratio. And also by simple algebra, you can calculate that even in adaptive data setup, this one is unbiased. So why do we discuss this particular estimator? Since if we are in a independent ID data scenario, this AIPW estimator has a semi-parametric efficiency, which means it has the asymptotically optimal variance as compared to all other non-parametric estimators, as long as we estimate this mu hat in a reasonable way. If the mu hat is consistent and converges to the true mean at a certain rate, and this one gives us almost the optimal estimator, okay, AIPW estimator. However, in adaptive data, if we are dealing with the adaptive data, the things become a little bit complicated. As we can see that in adaptive data, still the ET can decay to 0 over time, and this will cause issue also. And in one of our paper, we show that the variance of our gamma hat t in the AIPW score here is dominated by this inverse ET. And when ET goes to 0 over time, and this variance can explode, and which means our estimate can be very unstable. And that is why the AIPW estimator may also cause problem in the adaptive data setup. So how do we fix it? If we still want to use this AIPW estimator, but we want to use it in the adaptive data setup, and that is our approach. We can adaptively weight this AIPW estimator so that we can control each term's contribution to the final estimator. Intuitively, we can upload those gamma hat t who have the smaller variances, but we can downweight those gamma hat t who have large variances. And as an example here, we can the HT here denotes our adaptive weights, and as an example, HT can be proportional to the inverse standard deviation of our gamma hat t. Recall that previously the gamma hat t, the variance of a gamma hat t can is almost at this quantity, at the level of this quantity, and then we take the inverse of the root of this quantity, which means that we use HT to approximately standardize the AIPW score gamma hat t term by term. So and then we aggregate this approximately standardized t statistic, and we get our final estimate QPAT here. So is that clear? So gamma hat t, we analyze this conditional variance, and then we use HT to offset the potentially large variance caused by the issue of decaying ET here. And that gives us our final estimator, adaptively weighted AIPW estimator. And we also have a CLT for such adaptive weighting. So under some conditions, regularity conditions, and we have this, our estimator is consistent and asymptotic normal. And we also give the estimation of our variance, the variance, so that this will allow us to construct the confidence intervals around our estimation. Now I want to take a pause and try to understand why adaptive weights help during constructing the confidence intervals and also recovering the CLT. So in order to have a CLT, we should have three ingredients here. One is the infinite sampling, which means we should have enough samples, which allows us to go to a large sample region. And also we need to have bounded moments. That means our estimator should be well behaved over time. And we also need to have some recorrelation, such that the spurious fluctuations at the beginning will not influence later on experiment. But all of these can fail during an adaptive experiment. But how our adaptive weights helps. So the first two conditions here actually can be somehow remedied by some constraint on the assignment probabilities ET, as long as ET do not decay to zero too fast, and we can have these two conditions satisfied. But for the third one, it really also has it really is related to the true environment and also the outcome models here. As discussed by in Anand's talk, if the signal to noise ratio is too low, and it's very hard for us to just to recover the CLT. And so to understand why our adaptive weighting helps, we can go back. We can take a step back and consider a simpler setup, the multi-armed bandit setup. And here we do not have the context here, and we only have WT, YT. Our goal is to estimate the arm value QW here. So recall that our adaptive weighting scheme is to construct the reweighted AIPW estimator, and the gamma hat AIPW score can be written in this way. The mu hat T is from some direct method estimator, such as a sample mean estimator, and we use the inverse probabilities 1 over ET to correct the bias of the mu hat T here. And again, the variance can be characterized by the inverse of ET. And we, following the previous adaptive weighting scheme, we consider the case that where HT equals the root ET, which approximately standardizes the gamma hat T here. Let's go over the previous three ingredients: the infinite sampling, bounding moments, and recorrelation. As long as the assignment probabilities ET are not decaying too fast, and we can have the variance of our estimator goes to zero asymptotically, which means our estimator is consistent. And we also have the fourth moment of our T statistic goes to zero asymptotically, and by the recorrelation is satisfied by the design of our adaptive weights, since the variance of our T statistic converges to 1 in probability by construction here. So right now you may wonder if we have a more general adaptive weighting scheme other than choosing the adaptive weights HT to be the inverse, to almost be the inverse of the standard deviation of our AIPW score here. Here is a recipe. So here there were three ingredients, the first two can be somehow remedied by the constraint on the assignment probabilities. The third one really relates to the outcome model. And for the third one to be satisfied, we need at least various convergence condition to be satisfied. That is, this condition is to be satisfied. So the question becomes how we construct ways, the HT, to satisfy this condition. And in our paper, we introduced a state breaking procedure. That is, we can construct HT recursively such that this condition is satisfied by construction. To say that, we introduce a variance allocations rate sequence lambda t here. We can use this formula here to construct the HT recursively. So intuitively, lambda t represents a fraction of our remaining variance that we are going to allocate to this upcoming observation. So if we believe the arm is good, the arm is a good arm, and in the future the experimenter will pull this arm more and more often, which means we can also give larger portion to the future. So the lambda t can be small here. Conversely, if we believe this arm is a bad arm, and then we may want to put more weight, put more variance allocation to this particular upcoming observation, since in the future we may get very fewer samples from this bad arm. So the lambda t here can be large and close to 1. Particularly, there are two instances here. The first one is the constant allocation rate. That is, we set lambda t, so we allow equal part. So the future observations get equal share of the remaining variance, and such that the conditional variance of HT times gamma hat t is a constant, which equals 1 over capital T here. And this recovers our previous discussion of the adaptive weight selection, that is HT equals the root ET here. A second scheme is that is the 2-point allocation rate. If we have more information on the data collection mechanism, suppose suppose ET, the assignment probabilities represent the probability that we believe this arm to be optimal. For example, the Thompson sampling algorithm, and ET also is suppose it is lower bounded by some polynomially decayed floor here, and then we can design our lambda t as a convex combination of the of two regimes. The first one is when this arm W is optimal, and we assign the optimal oracle allocation rate lambda t to be the equal share here. And the second one is we believe this arm is suboptimal and will be dropped over time, and so the assignment probabilities will immediately hit the lower bound, and then we can also calculate these suboptimal arms the best the oracle lambda t here, and then we can use a convex combination of ET times this oracle for the optimal arm and 1 minus ET times this oracle for the suboptimal arm to get our lambda t. That is how we decide the 2-point allocation rate to, and then given this lambda t, we can construct the ways recursively by the formula here, HT. And as you can see, so this condition can be satisfied by construction following these two schemes here. And now I'm going to talk a little bit about our simulations. This is three.
Sorry to interrupt. If we can make it in 2-3 minutes, that will be great, so that we can also have some time for discussion.
Sure. Okay.
Thank you very much.
Yeah. So consider these three Onearmed Bandit algorithms, and the first column here is the unweighted AIPW estimator, the standard AIPW estimator, which means the HT equals to 1, and this column here is the sample mean estimator, and we calculate the variance, supposing that just use the empirical variance, supposing that we are using the ID data. And as you can see, when the signal to noise ratio is low, or if we have no signal, then these two do not give us asymptotic normality. But our adaptive weighted estimators recovers the normality. And again, and this is some statistics about our estimation. It's a huge panel here. I'll try to parse it a little bit. And the blue line here represents the unweighted or standard AIPW estimator. And as you can see, this gives very large variance, and as well as the mean square error, because it does not take into consideration that the bad arms is undersampled during the experiment. The sample mean estimator always gives us the estimates with smallest, almost smallest the mean square root error. However, we cannot guarantee its coverage just using a simple way. But here we calculate. We also compare our work with the Aditya's work, the confidence sequences work, and they have the coverage here, and as expected, and their coverages are always valid, but their confidence intervals are a bit wide as compared to ours. But here, our adaptive weighted estimators can have almost the good coverage with sample size growing, and also we have tighter confidence intervals. But again, here the Aditya's work allows for the valid coverage at any time, and they also allow for the adaptive stopping time. But here we consider the sample size is fixed and it's non-adaptive. I'm just wrap up here. So adaptive experiments can give us a lot of benefits because they are sample efficient to fulfill some particular objectives. But this also give us great challenges for the post-analysis, such as policy evaluation and also for policy learning, which is studied in our second work here. For the policy evaluation, we borrow the techniques of AIPW estimator from the causal inference literature, and we propose to adaptively weight these AIPW terms such that we can recover the confidence asymptotic normality and also construct the frequency-based confidence intervals. Yeah, that's pretty much of it. Thank you. Yeah.
Thank you very much, Rohan. Great. So now the floor is yours, Asaf. I will let you start the discussion. So please.
All right, thank you very much. And thanks to all the three speakers, to Rohan, Aditya, and Anand for their contributions. And thanks for the great questions. I was following the chat box all along, so there was some lively discussion there. And Rohan, I'm sure you're going to get some questions now also. There's a bit of a delay. People wait till the end of the talk, I guess, to ask the questions. So you'll probably want to monitor the chat box also to see that something's surfacing there. So one thing that I wanted to raise as a point, and I'd be really interested to hear your collective thoughts on this. We've seen as a common theme here that there are all sorts of challenges that come out from looking at data that basically have been sampled using an adaptive procedure. And we saw points that discuss both the sources of bias, potential significant distinguishing features between adaptive algorithms, and also ways to try to mitigate that by constructing more robust estimators. So given that, one question that I wanted to raise is, what do we do generally if we don't know the nature of, or we know very little about the nature of the scheme? And given the sort of divergence of possible effects this could have on the sampling mechanism. So in particular, one of these came up in Anand's talk, where we saw this really very significant departure between the behavior of Thompson sampling, for example, and UCB. But let's go back to the origins of the bandit literature. There's been a lot of initial work that was developed also from the standpoint of constructing optimal algorithms, not regret optimal, but actual optimal algorithms, like that led to the Gittins index and other works in that stream. How do those algorithms perform? How would data sampled using those mechanisms behave? Would the bias be more significant? Could these be corrected by appropriate adjustments to estimators and so on? So I'm just curious to hear your thoughts a bit on that, both on the specifics of the sort of that literature and the impact of those sampling schemes, and also in general, what do we do when we don't know that much about the nature of the sampling scheme?
Okay, I can take a first stab, and so you asked several questions in there. So from like, you can ask about types of estimators you can construct. Now, it turns out that if you don't know the sampling scheme, you can still construct estimators like sample mean type things. And under any adaptive sampling scheme and any stopping scheme, you'd still retain validity with confidence sequences. Now, if you know the sampling scheme, you can construct confidence sequences for AIPW type estimators or D-weighted type estimators. Essentially, we have a general central limit theorem to confidence sequence type reduction. Anytime you can prove a central limit theorem, you can actually derive a confidence sequence. And essentially, those confidence sequences then are able to wash away many of the details, in the sense of, it would apply for Gittins index, they would be valid for Thompson sampling and UCB and Gittins index and so on. So they give a stronger form of validity. So I think there are some trade-offs, in the sense if you know the sampling scheme, I prefer AIPW type estimators. And if you don't know the sampling scheme, you can even do things like sample mean, but you have to just be careful how you adjust for the variance and so on, but the confidence sequences do. So yeah, I think that's a great question. I'd be happy to hear.
I'll pass it to thanks, Aditya. I'll pass it to Anand and Ruan in a second, but actually this point came up in your presentation, Ruan, more explicitly about the basic qualifications of the sampling scheme. For example, sampling infinitely often from the various options. And one of the interesting observations about the sort of so-called optimal sampling schemes, a la Gittins and others, is that they have the very peculiar sample path behavior. In particular, because the optimization is done in the infinite horizon discounted framework, then the resulting schemes, for example, have a property that they may actually only sample a single arm infinitely many times. And in fact, there's an event with a positive probability in which that arm isn't the optimal arm. And all of that somehow is tied in both to the way that these sampling schemes are constructed and the objective function, which is an interesting topic also in and of itself, because we study various schemes and their data collection properties, but the original objective under which the algorithm was constructed is quite relevant here. And this is coming into play in this framework that the optimal sampling schemes like Gittins will develop their schemes under. So in that scheme, for example, there may just be, and going to Ruan's talk, there may be a sort of a breaking point there where you just don't sample infinitely many times, and then it's game over. There's no need to consider the moments or anything like that. There's just not enough statistical information to draw any reasonable inference. So that was sort of one of the points that I was interested to raise here in terms of like considering other algorithms, because we tend to be very fixated on the sort of UCB and Thompson sampling type algorithms when we consider adaptive sampling. But even those vary quite a bit. One can tune Thompson sampling. Anand, maybe you want to comment on that too, like if there are ways to tune Thompson sampling to get very different behavior than the type of behavior that you've shown.
Certainly. So I'll go back to your previous question first, like the one you had regarding the Giddings index policy. So in fact, as you mentioned that particular aspect, I just thought of this very recent paper by Daniel Russo et al. I think it's a very valid point that the Giddings index policy may not sample all the arms infinitely often, and which could lead to serious complications, as far as post-hoc inference is concerned. But then you could appropriately sequence the discount factor in the classical Giddings index policy, and that basically leads to a one-to-one reduction to the classical UCB policy. And so the asymptotics for UCB will basically then kick in for the Giddings index policy as well under appropriately sequenced discount factors. So that is probably a partial answer to what happens to in the specific case of the Giddings index policy. Of course, I'm sure the sort of the anytime valid confidence sequence, you could just deploy them regardless of carefully tuning the discount factors as such. So that was for the Giddings index policy. And yes, of course, for Thompson sampling, so like most sort of classical versions of Thompson sampling are sort of designed with this sort of goal that is baked into the policy design. And the goal is basically, maximization of cumulative payoffs over the horizon of play. And so what that naturally entails is sort of prior distributions that are, which are such that their variances do not scale with the horizon of play. So for instance, you could alternatively consider a sequence of systems which is indexed by n, which is the sample size, and the prior variance associated with the arms could basically end up being a function of n, which is the sample size. So basically, the point here is that if you sort of carefully tune the sort of the rates at which the prior variances vanish with the horizon of play in this sequence of systems that you're considering, you could end up having potentially very different behavior from what basically I sort of highlighted in my talk. So like all these sort of limiting asymptotic behaviors in Thompson sampling and most of these sort of Bayesian algorithms, which are highly sensitive to prior specifications or misspecifications thereof, it matters a great deal as to what is your starting point. So even the instability sort of results for Thompson sampling that I alluded to, which had like very nice, beautiful, either uniform on 0-1 limits or, this Dirac measure at 0 at half, occurring in the limit, those limits could potentially be different if you, let's say, started with a different version of the beta distribution as the prior instead of beta 1-1, which is the uniform distribution. So what would sort of like qualitatively tend to happen in that case is that your limiting distribution will tend to mimic some of those properties of a prior distribution. Proving those things, however, in full generality is like a different nightmare altogether. But then like that has been my rough sense based on sort of numerical observations, that I've seen so far.
Ruan, do you wanted to chime in on this as well?
Yeah. I just want to say that I totally agree that if we do not have much information on the data collection mechanism, it may be hard for us to do post-hoc analysis. But one point is that the first one in our algorithms or in our estimators, we need to assume a knowledge of the assignment probabilities, but we do not need to know much about how these assignment probabilities are evolved over time, based on updated over time, and we can estimate these assignment probabilities if we have batch sampling, and if we have the batch data, and we can use. We can estimate within a batch and try to estimate the propensities and the probabilities there. But also for the additive complete sequences work, I think they also satisfy as you have discussed. But I do have one question here for additive. So do we also need to know some, in order to build the complete sequences, do we also need to know some information about the outcome models here, or the variance, or some in order to have a tighter complete sequences?
Yeah, That's a great question. So yeah, so I'll just respond both to Asaf, who just pointed something out. There's no issue with confidence sequences with Git engine. So there's, even if you don't sample infinitely, even if there's a positive probability that you don't sample infinitely, because confidence sequences are non-asymptotically valid from 1 to infinity. So if you happen to sample a norm 38 times and never again, your confidence sequence at that time is still valid. And so you have inferential statements all through the experiment, including at stopping times, no asymptotic, no requirement for infinite sampling. All those come in when you want to prove CLT type results. You need some kind of variance to go to infinity. I mean, the accumulative variance to go to infinity, but you don't need that for non-asymptotic inference. So for Rohan's question, yes, there are these versions of as the confidence sequences that use the empirical variance in there. So you don't actually need to know like assumptions about the underlying distribution. You can actually plug in empirical variances, just like the central limit theorem. You'd use an empirical variance term. There are empirical variance-based confidence sequences as well, which give you anytime valid inference, but adapt automatically to the unknown variance. And so yeah, I think maybe the ones that you used were sub-Gaussian or something like that, and you need to know the variance parameter. But there are other variants in which you don't need to know the variance, that you use an empirical variance instead.
Great. So I guess the floor, as Nina said, the floor is also open for people from the audience to chime in as well and ask questions by raising hands.
Yeah, of course. It will be great also to hear your thoughts. I can see there is a hand raised from Andre.
Thank you.
Andre, please jump in.
Thank you. Yes, it was really great to listen to all the presentations and the discussion. I would have one question. I do not know exactly details about Bandit algorithm, at least ahead of the webinar, but the question relates to some problems general in causal inference related to, say, endogeneity issues. Would any different randomization schemes, say Mendelian randomization or similar find application here, or any other procedures related also to problems of some reverse causality or endogeneity that could possibly make some possible issues here? This probably relates to all three presentations in general. Thanks.
Sorry, I didn't really fully understand the question, partially because I didn't hear some of the words there. But if anyone else did, could you paraphrase the question?
The question is basically about the issues in the algorithms when you would have problems of endogeneity in the variables. You have adaptively collected data, but how to solve if such issues would arise, maybe by different computational schemes that you mentioned, or different algorithms, different sampling schemes. I briefly checked in the meantime Mendelian randomization, but I do not think it has been used so far in MAB. I hope I was heard, but
I think to my understanding, some of these issues could have connotations, in the context of, I mean, I'm trying to put on the multi-armed bandit hat on, and I think, some of those points might relate to the correlated arm settings where rewards are actually correlated across arms, or, time variant rewards, wherein what you actually end up observing is, let's say, a number of times a particular arm has actually been pulled. So like the rewards are actually endogenous with respect to the policy that is employed. So your observations, your sequence of observations is going to depend on what policy was querying what arm at what time. So I think it's a very interesting question. And I mean, at least to my knowledge, if you are in that kind of a general setting and you want to do, let's say, policy agnostic post hoc inference, I wouldn't really have any any paper or a pinpointed reference off the top of my head that would consider such a general setting. Obviously, when you want to do post hoc inference, you need to assume perhaps some nice properties at the distribution level, related to the arms, and at the population levels, basically assumptions like independence across arms and in time and so on and so forth. Perhaps some generalizations along ergodicity, but then if you want to make it endogenous, then I think the problem becomes really complicated, and I wouldn't really know how to sort of approach that.
Thanks. I just shortly add that I think that in his presentation, plenary at the Econometric Society World Congress in 2020, Guido Imbens, possibly the one will probably know, mentioned bandits as one of the most prospective machine learning algorithms also for econometrics, where such issues, as I mentioned, are frequently noted. Just that. Thanks.
Thank you. So if there are no other questions, I may have one last question for all the talks. First of all, thank you very much for the great presentation. Thanks, Asaf, for the great discussion that you led. And my question is related to randomized versus non-randomized policies, so randomized versus non-randomized algorithms. Possibly for the talks of Ruhan and Aditya, who propose basically some solutions for the inferential problem. Do you think that non-randomized schemes would fit into your solutions? And on the other side, for Anand, based on your work, it seems that UCB schemes will be a favorite approach because there seems to be this, there seems to be a convergence towards one half when you have small gap or null gap and so on. So it seems that they are more consistent with what you would expect. But there are a lot of issues, inferential issues from regulatory bodies and for even in causal inference that non-randomized schemes can be associated with some other forms of problems like confounding problems and so on. So what would you say in this case? Maybe something in the middle, like a randomized UCB. Do you think that a randomized UCB will still maintain what you proved in your talks, that you still converge to this one half? So this is my questions for you all.
Rohan, why don't you go first? Yeah,
I can go first. Yeah, for the it's a great question. So for the randomized experiment, because in our estimator, we need to have the list ET, the assignment probability forms to be in a denominator, which means that it cannot be zero for the arms. Otherwise, our variance just will go to infinity, and this will be an issue. And that is why we also place a floor on the assignment probabilities to let it to not be decay so fast, such that we can control our variance in a reasonable way. And this also excludes the UCB discussed by Anand, this algorithm. But I just want to mention it here that so while we want to use randomization here a little bit, so I also echoing to a question in a chat. I didn't have time to answer that. No, if we are in a Bayesian framework and we can and we have some prior or some confidence about our outcome models or about our data collection mechanism, and that is why we want to introduce a little bit randomness here, and we can also use this randomness to try to estimate ET in a distribution for the outcome model, or for yeah, just a little comment here. Yeah,
thanks.
Okay, I can go next. So yeah, I think that's a great question. And I want to differentiate between two different setups. In the classical multi-arm bandit setup, where everything's IID from each arm and independent and so on, and it's not contextual, there's no potential outcomes, then deterministic sampling schemes are perfectly fine for confidence sequences. Constructing them is perfectly fine. Randomized sampling schemes are also fine, in which case you can do reweighted techniques and so on. But if you're in a setup where context matters, you have a contextual bandit problem, or you're in a causal inference setting where there's potential outcomes, and you want to do inference on treatment effects, randomization is basically necessary for causal inference. And so in those settings, you want to not have deterministic policies. Otherwise, if you have a deterministic policy, you can actually, there are provable impossibility results for inference on average treatment effects and so on. So yeah, I think that's a great question.
That's a great point, I think. Thank you.
Thanks, Aditya. I think you in part answered some of the points I was going to touch upon, but then back to your original question, Nina, on if there exists some sort of customized version which sort of an algorithm which does a best of both worlds between deterministic algorithms like UCB and randomized ones like Thompson sampling, which would still retain some of the desirable properties like perhaps asymptotically optimal or near optimal performance, in so far as the regret is concerned, and some nice fairness properties, which UCB-like properties tend to enjoy, which I sort of alluded to previously in my talk. It is very much possible. However, it needs to be looked at, very carefully, because even for deterministic algorithms like UCB, you may end up having, departures from asymptotic normality. Like you may not have a full sort of functional central limit theorem type characterization of the diffusion limit process, which basically, leads to sort of invalidity of the the standard sort of Gaussian approximation, for large sample sizes. So what happens is, everything basically boils down to what kind of, even if you are using very nice deterministic algorithms, the choice of the optimistic bias term in basically, which is like a key design parameter in UCB algorithms, that basically determines whether or not you're going to have asymptotic normality or not. So just to sort of give you a very simple example, I described the classical UCB algorithm, which basically inflates the sample mean by an optimistic bias term, which looks like a square root of 2 log n, right? Now, whether you have 2 there or whether you have log n plus log n, that is going to create like, surprisingly, very sort of consequential sort of implications for what happens in the limit. From a first glance at it, it might look like a very small, like a very minuscule difference in so far as the policy structure is concerned, but then you may actually end up having a limit which is non-Gaussian asymptotically. So I think those design considerations are, they are very important to keep in mind when you're designing deterministic algorithms, especially when you have considerations such as fairness, like some balanced sampling properties that asymptotically, if my competing alternatives, treatment and control, are more or less similar to each other, then with a high probability on every sample path of the algorithm, I want my patients to be assigned to the treatment and the control group, almost in a balanced manner. Now, if you have such objectives in your mind, you better have a very sharp focus on what bias factors you're using in your UCB policies, because you may or may not have asymptotic normality in that. And like results from classical statistics may not necessarily kick in, even under UCB in those cases.
Right. Thank you very much. And thanks also for mentioning fairness, because I think fairness is another hot topic and it should be discussed more, even in the definition. I don't know.
Just a final note, Nina, on to Aditya's point about the distinction between IID and other processes. One should add, and maybe to this community it's less relevant, but of course the machine learning community, there's a big segment there that studies the so-called adversarial settings or individual sequence settings. Obviously there, without randomization, there's not a lot of hope. So the real value of randomization comes into play in those types of settings. But we've seen it basically in other settings which are actually IID, like the load balancing settings that show, for example, results like the power of 2 randomization, which actually was also used in the best arm identification literature. So there's a transfer of these ideas, and there are settings where you can provably establish that the randomization is essential to improving the results. And again, that literature comes from a very different direction from the load balancing area, but it's been transplanted over to some extent also into the bandit literature.
Right. I think there should be a lot of cooperation between different literatures. And yes.
So I just want to add one final note here. So also in the setup of if we have a lot of arms, we have a lot of lamps. Even exploration can be a little bit costly, and in that scenarios, maybe people are considering exploration-free algorithms and also some deterministic algorithms. Yeah, that is just my final thought here.
Okay, so thank you, everyone. Sophia Villar wanted to send you greetings for her to everyone because she had to leave earlier. She made some questions in the chat. And thank you also for the people who asked questions in the chat. It was great. Thank you for answering in that. I don't know, Andre, if the questions will be shared in the YouTube somehow.
Yes, I was also wondering. I put a note on the YouTube, but there was no question, at least a few minutes back on YouTube. Maybe there were possibly some unanswered questions. Maybe we can also recap this in the YouTube recording.
Maybe. Okay. Thank you. That will be great because there were great questions and maybe people will benefit from looking at them. And I don't know if there are other questions from the chat. If not, I will just say thank you to everyone and a big bye. Hope to see you again.
And thank you very much.
Thank you again for the
I just add one final note. As you noted, the webinar was recorded and live streamed and will be available probably in a few minutes time on the YoungStatS YouTube channel. So available for all.
And thank you, Nina, for organizing the session.
Thank you for accepting my invitation, our invitation. Thank you for the great discussion and have a good day especially for those who are in the US and Ruan will join at 7 a.m. Thank you.
Thank you very much.
Thank you.
Thanks to all.
Bye.
Bye.